Now let's consider how flow and head are affected by the resistance to flow that occurs when we connect the pump to delivery piping at an oil terminal. Resistance to flow is affected by various factors, including the height of the reception tank above sea level and the distances covered by connected pipelines of varying diameters and configurations. Before we start the pump, we open the valve from a cargo tank containing crude, and the liquid flows through the stationary pump. This settles at a level that exerts pressure on the pump itself. We call this static discharge head. When we start the centrifugal pump and flow begins, head starts increasing above the static discharge head as can be seen on the discharge pressure gauge. As the pump rotational speed increases, the head increases above the static discharge head and changes in proportion to the square of the flow rate developed. This can be shown as a curve on the HQ graph axis, and we call this a shore resistance curve. In fact, there are a wide range of shore resistance curves covering the different pipeline configurations at terminals. These curves model how flow rate and head change with increasing pump speed across the range of terminal delivery pipeline systems. When the shore reception pipeline arrangement is restricted, the shore resistance curve will be very steep. With a high shore resistance curve, the head develops at a greater rate than the flow rate. With a low shore resistance curve, the flow rate develops at a greater rate than the head. If we now overlay the pump performance curves over a shore resistance curve, we see how flow and head increase as our centrifugal pump rotational speed increases for a particular discharge condition.